Hello students, today we are going to cover section 7.1, ions, pages 187 through 193. I saw this little comic, so to speak, and I thought it was kind of cute. So, pyrite. Pyrite is what we call fool's gold. You probably have heard of that. The chemical formula for it is FeS2. Pyrite is a crystalline solid. Particles are arranged in an orderly, repeating fashion, and it can be used as a source of sulfur when making sulfuric acid. So in this chapter, we'll discuss how ions form from neutral atoms. We actually covered a lot of this in the last chapter, but we're going to be kind of reviewing that and then going into a little more detail. The objectives we are going to cover: determine the number of valence electrons in the atom of a representative element, classify elements whose atoms tend to gain electrons and those that tend to lose, describe how cations form, explain how anions form. And again, we've covered a lot of this. We've touched upon a lot of this in the last chapter. So we're going to talk about valence electrons, and I started using that term in the last chapter. Valence electrons, the electrons in the highest occupied energy level. Okay, the highest occupied energy level. Let's underline that. Of an element's atoms. The number of valence electrons largely determines the chemical properties of an element. And here we see the pictures. This has one valence electron, two. This has a total of 3 electrons. However, we have one valence. We have 4 valence electrons here, 5 here, and sodium has 1 valence electron. These are how many protons this has. Sodium has 11 protons, nitrogen has 7, carbon 6. Okay, so those are the number of protons. And here we can look at these valence electrons. Let's take a look at, let me just box them in here. Here, this has 4. This has 1. So these are what we call valence electrons, highest occupied energy level. To find the number of valence electrons in an atom of a representative element, you look at its group number. Again, this is not news. We've talked about this before. It's group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Also, if you count from 1 through 18, you could just subtract. This would be 13, 14, 15, subtract 10, and that'll give you the group of the valence number also. If you go 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You might see that in some periodic tables. So again, group 2A would have 2 valence electrons, and we've seen these pictures in a couple. Here, magnesium has 2, calcium would have 2. 7A, again, would have 7 valence electrons. And we've talked about this. We should be getting a handle on valence electrons. Carbon and silicon, group 4A, has 4 electrons. Helium has 2 electrons. The rest of the noble gases have 8 electrons. So valence electrons are usually the only electrons used in chemical bonds. So when we're talking about chemical bonds, we're going to talk about just the valence electrons. We're really not interested in the filled energy levels. Only the valence electrons are shown in what we call electron dot structures, and that's what I have on the bottom here, electron dot structures. And this would be the valence electrons. We write the symbol and we put these dots in. we go around and then we start doubling up. Kind of like square dancers. You have, here you can see it, 2 here, 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 and here. That's how you put it. You kind of square it off as if it was a square. Here you can, see how it's kind of written. And here's a few. So lithium, this is group 1A. And you see their 1 valence electron. Let me just write 1A there. This would be 2A, 3A. Okay, so to write these electron dot structures, sometimes they're called Lewis dot structures. So I might refer them as Lewis dot structure, electron dot structure. We're talking about the same thing. These are diagrams that show valence electrons as these dots. So you see these dots here. 3A, this would have 3. And I use this when showing bonds. When we start talking about bonds, I will be using these electron dot structures. So the octet rule. Again, I mentioned it in the last chapter. Here it officially kind of introduces it. It's forming compounds. In forming compounds, atoms tend to achieve the electron dot configuration of a noble gas. Okay, so electron dot configuration of a noble gas. An octet has a set of 8, just like an octave in music, it's 8 tones. An octet would be a set of 8. A noble gas has 8 electrons and its highest occupied energy level and is stable. And that would be, again, when we talked about the noble gases, that would be S2P6. Both sub-levels are full. The octet rule applies to most atoms in compounds. Okay, so now we're talking about the octet rule. Again, if we look at this, valence electrons, let's say we look at lithium. Lithium would want to lose that. Oh, let's look at, okay, boron. No, let's look at fluorine. Okay, fluorine, we're going to gain an electron. Okay, if we gain an electron, it's going to have 8 electrons in the highest occupied energy level, and it have the same electron configuration as neon. Okay, the octet rules that have neon has 8 valence electrons, and any of these in this row, okay, period 2, would be have the same number of electrons or electron configuration as neon. If we would, well, if carbon would share electrons, here boron was going to lose. Actually, these will be the noble gas in the period before it. These would be the same noble gas in the same period. Okay, so neon has a total of, it has 8 electrons in the highest occupied energy level. Again, we've seen this, the octet rule. We would tend to lose this electron. And notice we have 8 electrons in the next level down. And so now it's happy. It has 1 extra proton, without an electron, so it has a +1 charge. Magnesium is going to lose 2. And again, we've seen this slide before. And here it has 8 electrons. Okay, so magnesium would have the same electron. It has a total of 10 electrons. And if you look at neon, neon has 10 electrons. So magnesium would have the same electron configuration as neon. Okay, and let's just write that there. Magnesium is the same one as neon. If we look at potassium, Okay, potassium is in group 4. It would have the same electron configuration as argon, which was 18. Okay, so potassium would have the same electron configuration as argon. Potassium is in group 4. Any of those pluses, they're losing them, and so they're going to go back a period, so it would be the same as the noble gas in period 3. Okay, this would be neon. Atoms of some nonmetallic elements tend to gain electrons to share electrons with another nonmetallic element to achieve a complete octet. So here it's going to gain an electron, so it has an extra electron. Chlorine would have the same electron configuration as argon. Okay, we'd have the same one as argon. Which would be a total of 18 electrons. So atoms of metallic elements tend to lose their valence electrons, leaving a complete octet in the next lowest energy level. Here we see the valence electron lost. Okay, we lose the 4s1, and so here is the same electron configuration as argon. Notice the next level down is full. Magnesium loses this, and so now it has the same electron configuration as neon. Again, this is all full. It has 8. 6, 2 plus 6 is 8. 8 here. So see, like 10 electrons would be the same as neon, 18 electrons would be the same as argon. So we lose this valence electron. Those are metallic elements. Atoms of nonmetallic elements tend to gain electrons or to share electrons with another nonmetallic element to achieve a complete octet. And again here, notice 5 goes up 1, 6. It has 18 electrons, same as argon. This goes up 3. It has 10 electrons, the same as neon. Again, nitrogen has gained 3 electrons, so now it's complete. The p orbital has 6, s has 2. Same as neon. This one is the electron configuration is same as argon. So nonmetallic gains, forming anions. Atoms loss of valence electrons produces a cation with a positive charge. And again, here we have sodium is a positive charge. Sodium has the same electron configuration as neon. Here's neon's electron configuration. So here's some equations which we didn't do. We have magnesium with the 2 valence electrons, and we have magnesium now has a +2 charge, and here are the 2 electrons that have been removed. Sodium has 1 electron, and now we have an ion. Okay, notice this would be the neutral atom, so we have the valence. We don't put the 8 electrons here. We just put the plus. And here we have that 1 electron. So here you have that 1 electron that sodium has lost. Now notice here we have the plus electrons on this side of the arrow. Here, it's on the right side of the arrow. That means this is being released. This is what we start with. This is what we end up with. We have 2 electrons being released, and we have magnesium with a +2 charge. We have 1 electron being released. We have sodium with a +1 charge. Here, we're adding 1 electron. And so now we have chlorine, and here we can show it with the 8 electrons. I did a different color of the new electron. Normally it would have 7 electrons, 2, 4, 6, 7, and then I put in the 8th one as a different color. So here's a way to write some of these equations of losing. We would use the electron dot structure And then here we would see about losing electrons, or here we're gaining electrons. See the plus, that electron is on the left of the arrow, and here it's on the right side of that arrow. So now we have some exceptions to the octet rule. Some ions formed by transition metals do not have noble gas electron configurations. So we're going to be talking about some of these transition metals. So some ions formed by transition metals do not have the noble gas electron configuration, S2P6. Would not have that, and this is, again, transition metals. We call them pseudo noble gas electron configuration. So let's take a look. This is silver. Okay, this is silver. We have a lot of orbitals here. We would fill up, silver would have, remember, we actually would fill up S1 before D10. However, this is more stable than S2D9. So this would be the electron configuration, and we're going to look at this and this. To achieve a noble gas configuration of krypton, it will have to lose 11 electrons. Okay, with krypton, we want the S2P6 full. So we would have to lose the D10 and the S1. That's where we get that 11 electrons. We would have to lose those two. Okay? We would have to lose these two, and then we would have the electron configuration here of krypton. So, which is unlikely? It's really a lot of electrons to lose. So what happens is it actually loses one electron, the 5s, and the configuration that results, all of the orbitals are full. Now we have S2P6D10 orbitals. We have these full, and I have these in blue. They're full. It's not the electron configuration of noble gases, which is S2P6. This is S2P6D10. So this is called the pseudo-noble gas electron configuration. We have 18 valence electrons. This is those 18 valence electrons. So you would lose the s orbital. So here's that 18. 10 plus 6 plus 2 is 18. Some examples of pseudo-noble gas configurations: gold with a +1, cadmium with a 2+, and mercury with a 2+. These are some other examples. This one is silver. Okay, so pseudo-noble gas electron configuration has the highest occupied energy level, does not have 8, it has 18. And S, P, and D orbitals are full. Okay, the gain of a negatively charged electron by a neutral atom produces an anion. When we name, we're going to go into a chapter where we will be naming ions. Okay, the name of an ion of a nonmetallic element ends in IDE. So we would have a chlorine atom. It forms a chloride ion. Okay, it forms a chloride ion, or we call it chloride, like sodium chloride. Oxygen atom forms an oxide ion. So we take part of it, the first part, put an IDE, so it would be oxide. But nitrogen would be nitride. You add in sulfur. Let's do a couple examples. Nitrogen atom, nitrogen ion would be nitride. Sulfur would be a sulfur atom or sulfide. So we use the IDE to name the anion. The cation, we keep it it would be sodium ion. We don't say sodiumide. We just say sodium for cations. Magnesium would be magnesium ion. Beryllium would be beryllium ion. Only for the anions do we use IDE. The cations, we just say, like I said, sodium ion or potassium ion. So anions have relatively full valence shells. Atoms of nonmetallic elements attain noble gas electron configuring more easily by gaining electrons than by losing them. And again, we've talked about this before. Here we see chlorine gains an electron, and it has the same octet as argon. Here we have some examples of ions, and let's check off monatomic, meaning here we have fluoride, chloride, bromide, iodide. Notice these have IDE endings, and I'm just doing the ones with just monatomic one atom. And let's look at oxide, sulfide, again, IDE endings, and nitride, phosphide. Again, those are just one. Now the others, these are polyatomic ions, and I'll box those in another color. Let's do blue. These are polyatomic ions, and those have a different set of rules. This was an exception to that rule, even though it has an IDE. We have eights. Here we have eights. Okay, sulfate, carbonate. These are groups that kind of, I call them gangs, that are always together, and they are polyatomic anions. But for now, these are some examples of monatomic that we're talking about. Again, all IDE endings. Halide. A halide ion, ions that are produced when atoms of chlorine and other halogens gain electrons. These are halogens, and we call them halide ions. Some groups have just special names. All halogen atoms, group 7, have 7 valence electrons and need to gain only 1 electron to achieve that electron configuration of a noble gas, an octet. And so here we see fluoride, chloride ion, bromide, and so on, iodide. Astrodide. Okay, so here are these halide ions. We really don't use this a lot. We usually use these 4. So to find the number of valence electrons in an atom of representative element, look at its group number. Atoms of the metallic elements tend to lose, metallic elements tend to lose their valence electron, leaving a complete octet in the next lowest energy level. Non-metallic elements, some non-metallic tend to gain electrons or share electrons with other non-metallic elements to achieve a complete octet. Atoms loss of the valence electrons produces a cation. Gain of electrons by a neutral atom produces an anion. So homework assignment, read pages 187 to 193, and this is section, I don't have it written down, this is section 7.1. Okay, section 7.1, pages 187 through 193.